Swayam Prabha. Digital India. Educated India.
We are going to continue our discussions on generalized coordinates, constraints, generalized and the configuration space that we had introduced in the last lecture. We are going to look at these concepts once again and with examples. Just to recapitulate, the configuration space is the space in which a single point fixes the configuration of a dynamical system, and the coordinates that are used in the configuration space are known as the generalized coordinates. And the definition of generalized coordinates, very important, the minimum number of independent variables that are required to fix the configuration of a dynamical system, and in which space? In the configuration space. A change in the generalized coordinates indicate dynamical paths. We had looked at this example of a rolling coin, and these were the, we started off with the physical coordinates, which were the location of the center of mass and the orientation of the coin and the spin of the coin, angle of the coin. Then we found that for all to be always in ground contact, the z coordinate of the center of mass must satisfy this constraint, which is in terms of the coordinates. These are called holonomic constraints, and we had non-holonomic constraints or non-integrable constraints in terms of the coordinate rates, the time rates of the coordinates. And then we found that the generalized coordinates were only 5 in number. By specifying these 5 coordinates, I can completely fix the position and orientation of the coin. Therefore, we have 5 degrees of freedom for the coin. In this discussion now, we will discuss this further, and I will present an alternate formulation, which makes the representation quite simple. In this formulation, I will look at coordinates of the contact point rather than the center of mass, coordinates of the center of mass of the coin, which are of course very important, because finally that is what will be used in the equations of motion. But if we can simplify the representation of constraints, etc., that would be of much help. Therefore, we try to look at an alternate formulation using the coordinates of the contact point on the ground, x, c, y, c. These are the coordinates of the contact point on the ground, and x, c, y, c is measured in the x, y, z coordinate system. Therefore, the contact point coordinates and the rest of it remains the same. The orientation and the spin coordinate, they remain the same, psi, phi and theta. These were the two no slip or pure rolling constraints, the constraints that represent pure rolling or no slip. This we had derived in the previous lecture. Now, we are going to reformulate these constraints in terms of x c and y c. Rather than using the velocity of center of mass, let us see how we can modify in terms of the present choice of coordinates. First, we represent the position vector of the center of mass. Position vector of center of mass, suppose I have this origin as O, this point is of course C, and G is the center of mass. Then I can write OG vector is equal to OC vector plus Cg vector, and that is what I have written here. The position vector Rg is equals to Rc, Rc is the position vector of C, plus Cg, Cg is along the radial direction in the coin from the contact point to the center of mass. We will start writing this position vector of center of mass in x, y, z using the unit vectors I cap, j cap, k cap, and that is equal to x c I cap plus y c j cap. This is nothing but the position vector of point C plus C g. Now, how do I represent C g? C g can be represented very conveniently using the rotation matrix. We have we derived the rotation matrix expression here. I have written in green. We have derived this, and if I multiply this rotation matrix, so this rotation matrix takes us from the primed frame to the ground fixed frame x, y, z. If I therefore multiply here any vector in the primed frame, what is the vector C g? C g has a magnitude r and a direction along the z prime. Therefore, this must be 0 0 r, and if I multiply with this rotation matrix, I will get C g in x, y, z. The representation of that same vector C g in x, y, z coordinates. And if I do that, I leave it to you to complete the final details. I get this expression of x g, y g, z g. Now, you see x g, y g, z g is in terms of, these are in terms of x c and y c, and of course, psi and phi and the radius of the coin. Now, we can start differentiating this. We derivate this with respect to time and obtain the velocity of center of mass. Everything now represented in x, y, z, the ground fixed frame, and substitute these velocity expressions in our constraints. The constraints are sitting here. Substitute these expressions of x g dot, y g dot, there is no z g dot of course, these two expressions you substitute in the equations of constraints, and what do you get? If you substitute these in the equations of constraint, you get very simple form of the constraint equations. Once again you will find they cannot be integrated, because psi, theta, these are all functions of time. Psi is a function of time, and we cannot integrate this without further information. These two are now the new constraint equation in our new choice of coordinates. So, what do we have? We have the new coordinates x c, y c, psi, phi, theta. X c, y c are the contact point coordinates. Always in ground contact, this is already taken care of, because z g has been replaced. I can find out the z coordinate of the center of mass just by using these coordinates that I have chosen now. And the no slip constraint, they are replaced by these two very simple looking constraints in terms of x c dot, theta dot and psi. Now, that simplifies to a great deal our representation of constraints in the new coordinate system or new coordinates, choice of coordinate, the coordinate set. Therefore, we have these coordinates, the non-holonomic or non-integrable constraints, and the coordinate transformation which we will be needing to now find out. Using these coordinates, I can now find out anything about the coin. I can find out the center of mass, for example, of the coin, and orientation I can definitely find because the rotation matrix is known to me. So, that completes the rolling coin problem alternate formulation. Now, we move into a discussion, a more detailed discussions on coordinates and configuration space. We have looked at some examples. Now, you have some idea of what are coordinates, what are generalized coordinates, what are physical coordinates, what is the configuration space. Now, all these ideas now we have. Now, we will generalize. Now, we will talk in more general terms. Now, physical coordinates are useful for position, velocity, acceleration representation. For example, center of mass, position, velocity or acceleration, which we will require in the equation of motion. They are the physical coordinates. But generalized coordinates, as we have seen in the coin example just now, generalized coordinates need not always represent that center of mass coordinates. They need not include the center of mass coordinates, but there should be a mechanism to find out the center of mass coordinates. Otherwise, generalized coordinates can be anything. So, physical coordinates we will represent as R, R1, R2 up to Rm. There are m physical coordinates. Suppose we have m physical coordinates, we are now generalizing things. We have m physical coordinates. So, suppose we have x g, y g, z g of a body, the center of mass coordinates, then they become R1, R2, R3, and orientation, suppose another 3 coordinates psi, theta, phi, let us say yaw, pitch and roll, then they will become R4, R5, R6. So, R1, Ri will represent a generalized a physical coordinate, R will represent physical coordinate. Now, we may have constraints over these physical coordinates, as we have seen in the pendulum example, for example, as an example, or even in the conical pendulum example. On the physical coordinates x, y, z of the conical pendulum, we had that constraint x square plus y square plus z square is L square. We can have constraints. Constraints are of these two types: holonomic, which are explicitly in terms of the coordinates, like in the conical pendulum, it is x square plus y square plus z square equal to L square. We have constraints explicitly in terms of the coordinates. Now, holonomic constraints are further subdivided as scleronomic and rheonomic. In scleronomic constraints, if a holonomic constraint is scleronomic, it means that there is the constraints do not involve time. The constraints do not involve time. That means, it is only in terms of the coordinates, only the physical coordinates R1 to Rm. There are m physical coordinates, the constraints are in terms of the coordinates. There can be a number of these holonomic, scleronomic constraints, basically scleronomic constraints. When we say scleronomic, it automatically means it is holonomic, it has to be. So, we can have, let us say, m minus n constraints, m minus n scleronomic constraints. What are rheonomic constraints? Rheonomic, okay. So, example, so pendulum, we have the physical coordinates R1, R2 as x, y, and we have this scleronomic constraint that R1 square plus R2 square minus L square equal to 0. So, that is an example of scleronomic constraint. Rheonomic constraint, when the constraint involves time explicitly, when the constraint involves time explicitly along with the physical coordinates, of course. We can have a certain number of rheonomic constraints. We had this example of pendulum on a cart. R1, R2 are these physical coordinates x and theta, location of the cart and the angle the pendulum makes with the vertical. And we had this rheonomic constraint that R1 minus u as a function of time, which is of course specified, is equal to 0. For example, if the cart is oscillating sinusoidally, so ut can be sin omega t, some a sin omega t. Okay, when it is explicitly specified, then we have this rheonomic constraint. The second type of constraint is the non-holonomic constraint, and we have already met the non-holonomic constraint variety while discussing the rolling of a coin. Non-holonomic constraints are involved, they involve the time rates of the physical coordinates in a way that they are not integrable. Of course, if they are integrable, then I can get back the constraint in terms of the coordinates, the physical coordinates, but they are non-integrable, and that makes it very special. Therefore, non-holonomic constraints are basically constrained in terms of the time rates of the physical coordinates, but they are non-integrable. We cannot get back to a holonomic constraint, then only it is a non-holonomic constraint. We cannot write it as we cannot integrate it and write it in terms of the physical coordinates themselves. We cannot get rid of the time rates of the physical coordinates. This is one form of non-holonomic constraint where it is in terms of the physical coordinates and their rates, non-integrable, and in general time. Example is of course the rolling coin. We had the physical coordinates r1, r2, r3, r4, r5 which are also generalized coordinates, and we had these non-integrable constraints C1 and C2 as written here in terms of the physical coordinates or even the generalized coordinates. There is another type of non-holonomic constraints which are of inequality type. An example is like this carom board coin of diameter d, let us say it will move on the carom board, and the center of that coin can move only within that dashed square. If I represent as physical coordinates x y of the center of the coin, then the constraint that I have on the coordinates r1, r2 which represent the center of the coin as mod of x plus or mod of r1, basically mod of x plus mod of y minus a is the side of the carom board, length of side of carom board, a minus the diameter of the coin divided by root 2, and that must be less than equal to 0. This is a non-holonomic constraint, it is an inequality constraint, and that is a non-holonomic, that is classified as a non-holonomic constraint. Now, we come to generalized coordinates, that will be represented as q using q, lowercase q, q1, q2 up to qn, n generalized coordinates. If I have m physical coordinates, then I should be able to represent these m physical coordinates in terms of this n generalized coordinates and in general time. Definitely m must be greater than equal to n. The number of physical coordinates must be greater than equal to the number of generalized coordinates. Now, configuration space is defined using the generalized coordinates as we have already discussed. The degree of freedom of the system of a dynamical system is same as the dimension of the configuration space of the dynamical system. This we have looked at. The degree of freedom, which is the dimension of the configuration space, is equal to the number of physical coordinates, the number of physical coordinates we have at hand minus number of holonomic constraints. Non-holonomic constraints do not reduce the degree of freedom of a system. For example, the car, we had the rolling constraint of the wheel. We cannot arbitrarily move the car, but I can drive a car and take it to any arbitrary configuration. There is no constraint. I can take it to any location on the plane and in any orientation. I can drive it to that specified location and orientation, but I cannot follow, I cannot push it, I cannot just slide the car to that orientation, that is not allowed, that is not a dynamical path. Therefore, this non-holonomic rolling constraint etcetera, these are non-holonomic constraints, general rolling constraint is a non-holonomic constraint. They do not reduce the degree of freedom of the system. I will, in the case of the car, I will still need these 3 coordinates, the location and its orientation, to completely specify the configuration, even though I have this non-holonomic constraint that I cannot slide the car, I cannot push the car arbitrarily. But holonomic constraints do reduce the degree of freedom. Like in the coin example, the z coordinate of the center of mass, that was related to the tilt of the coin phi, and that helped us remove zg from the list of coordinates and get a reduced set, and it had 5 degrees of freedom. So, 6 minus 1 holonomic constraint, 5 degrees of freedom, and 2 non-holonomic constraints, 2 no slip conditions, they do not reduce the degree of freedom. We will still require these 5 things to be specified to completely fix the orientation of a coin. The contact point location xc yc, the direction of motion of the coin psi angle, the tilt of the coin which is the phi angle, and the how much it has spun, the theta angle. This I cannot reduce by including the non-holonomic constraint. Therefore, the coin has 5 degrees of freedom, and additionally it has got these 2 non-holonomic constraints. Therefore, degree of freedom, which is dimension of the configuration space, is equal to number of physical coordinates minus number of holonomic constraints. Suppose we have m physical coordinates and m minus n holonomic constraints, then we have n degrees of freedom, and these many generalized coordinates we will need. These many generalized coordinates we will need. So, n generalized coordinates we will need. For example, in the case of pendulum, we had one non-holonomic constraint, we had therefore reduced our configuration space to 1 dimension, which is represented by theta. We had 2 physical coordinates x y, location of the bob, m is equal to 2, and we had how many holonomic constraints? 1, x square plus y square is L square, 1 holonomic constraint, m minus n is a consolidated thing that represents the number of holonomic constraints, that was 1, therefore, degree of freedom is 2 minus 1, 1. In the case of the coin, we had 6 physical coordinates, the 3 location of the center of mass coordinates xg, yg, zg, and the 3 angular coordinates psi, phi and theta. We had 1 holonomic constraint which was relating zg in terms of phi, and therefore, we have 5 degrees of freedom, and our generalized coordinates are xc, yc, psi, phi and theta. Let us try to picturize this. We have m physical coordinates, n generalized coordinates where n is definitely less than equal to m, and there is a mechanism, there are relations, algebraic relations that relate the physical coordinate to the generalized coordinates. This we must have, because all our dynamics will be represented using the generalized using the physical coordinates to start with, but then we are going to switch to generalized coordinates. Therefore, we should be able to represent the physical coordinates in terms of the generalized coordinates. The physical coordinates form a space. Here I can show only 3 physical coordinates r1, r2, r3 arranged like in a Cartesian space. We can imagine this, we can visualize this, picturize this like this, that a point in this space represents the physical coordinates of a dynamical system. But can we choose arbitrarily these physical coordinates? No, because there are holonomic constraints, and holonomic constraints are represented as surfaces in these in this physical coordinate space. In the physical coordinate space, these surfaces, there can be more than one, of course. Here I have shown only one holonomic constraint. It represents a surface on which the point which represents the dynamical system must move. You cannot have arbitrary choices of the physical coordinates. It must respect that constraint, holonomic constraint. Therefore, that holonomic constraints are surfaces, hard surfaces on in this physical coordinate space. On this hard surface on which the points must move in the physical coordinate space, we can parameterize or we can coordinatize the surface, and what we are doing is we are coordinatizing using the generalized coordinates. So, I can again think of a Cartesian space sitting inside on this surface represented like this q1 and q2, that coordinatizes or parameterizes this surface, and hence these are our generalized coordinates. And any choice of these generalized coordinates, the choice of generalized coordinates is absolutely free. You can choose generalized coordinates arbitrarily, whereas physical coordinates you cannot choose arbitrarily. Therefore, the space of the generalized coordinates, which is the configuration space, is represented in this particular situation by q1 and q2. This is the configuration space of the system. This is how we picturize or visualize the physical coordinate space, the constraint, holonomic constraint, and the generalized coordinate space or the configuration space of the dynamical system. Non-holonomic constraints are not surfaces like this, and that is why they do not take away degree of freedom. Non-holonomic constraints are something like this, that at this point you are allowed to move only in this direction, but you can arrive at this point in some other way as well. You can arrive at this point in some other way. You cannot move on this path. This is forbidden. This straight line between this and this is forbidden. This is not possible. Let us say if you have one non-holonomic constraint, then what happens? You possibly cannot move. You possibly cannot move on this path. That is forbidden. This is a forbidden path. But since you can move in that red arrow direction, you may possibly be, you can move possibly like this. You can go to any configuration. You can go to any configuration. That is not restricted by a non-holonomic constraint. But at a point there can be local directions in which you can move, and if you can judiciously change your directions as you move, then you can relocate to any other point. There is no restriction on where you can relocate. Like in a holonomic constraint, there is definite restrictions. You cannot have arbitrary choice of physical coordinates. It must be on the choice of physical coordinates are valid as long as it is on the surface. But for a non-holonomic constraint, there is no such constraint, but maybe a direction. You cannot move in arbitrary directions in a special direction, but you can reach any point. There is no restriction on choice of points. So, to summarize, we have looked at the configuration space and generalized coordinates in more details, and constraints. We have classified constraints, and we have understood how to visualize or picturize the physical coordinate space, the generalized coordinates, holonomic constraints and non-holonomic constraints. With that, I will close this lecture.